happy to be back. I was here for the first time last year. I'm William Cook from the University of Texas at Austin, and I am going to talk to you about hybrid partial evaluation, which is joint work with my student Amin Shali, who was very fortunate to get a Best Student Paper Award at Uppsala a couple of years ago, but then for various reasons decided to quit academia and go into industry, and so he's not working on this anymore. But I think that I'm trying to continue it, so we'll see. Just a little bit about me. I did my PhD at Brown in '89, working with Peter Wagner on semantics of object-oriented languages and fun stuff like that, mix-ins, you may remember. And then I actually dropped out and became a software developer and worked at Apple and did AppleScript, and then I did an enterprise software company startup that almost made a lot of money. And then it was actually at that company we were experimenting with model-driven development of enterprise systems starting in 1999, actually. And I think a lot of other people were too. But I got really interested in that idea and wanted to do research on it instead of just do startup mode. So that's actually why I came back to academia in 2003. And then this project on partial evaluation is a spin-off of that idea. So I'm looking at partial evaluation in a very general sense, and I'm not a sort of dyed-in-the-wool partial evaluation expert. I'm actually a person who came to this field very recently, and it was like coming to a ghost town in a way, because there were all these buildings and beautiful things, but there was nobody living there, and the tumbleweeds were blowing through, and it was because partial evaluation was a very active research area for many years and had a lot of great results, but it was kind of dying out. And so I think that, maybe my coming in with a fresh perspective, I'm giving it a little bit of a new, and I think a lot of other people are too. There's a lot of talk of partial evaluation here. And so basically the field is being revitalized, but in a new style, and maybe not based on the sort of theoretical motivations that it had originally. But the goals are quite general, actually. We want to write very general programs and libraries that apply to many, many cases, and we want to use them in very specific situations to do particular jobs. And there's this notion of the sort of abstraction penalty, that the more general you make code, the slower it gets. Even when you use it in a specific way, you're using this very general code, and so you can end up with some extra penalties there in terms of performance that would not be present if you had just hard-coded your particular algorithm. And so we see that all over the place. And as we make more and more sophisticated libraries with more and more kind of general intelligence in them, this is a problem, because we'd like to make those libraries, and we'd like to do it without paying the penalty in the long run. And so one thing that partial evaluation can do, it's one technique that's able to specialize a general program to a specific situation. My goals were to make a kind of partial evaluation that's easy to understand, easy to implement, and actually does what you want in practice. And one of the problems that I think the partial evaluation researchers found, the sort of previous wave, was that partial evaluation was very powerful, but it tended to be somewhat uncontrolled. And so what that meant is that sometimes it would do great things, other times it would do nothing at all, and other times it would just make a mess of your program and make it slower, or make huge amounts of code without making it any improvement in speed. And so the lesson, if anything, we've learned from C is that having a clear performance model is super important, even more important than all kinds of other beautiful things that we would love to have, right? And so we'll put up with a lot of crap in order to get a clean, clear, predictable performance model. And so anyway, I'm trying to make that happen for partial evaluation. So here's an example. I'm going to go through a couple of these slides kind of in warp speed in a second, because I did them in the workshop yesterday, I kind of did a tutorial on this. But in case you weren't there, I'm just going to do quick level set so you know what I'm talking about. Here's an example of partial evaluation of a classic example. The power function raises x to the nth power. And if you know n, then you can specialize the power function. And the interesting thing is that if n is known, then, for example, this condition can be evaluated in advance. Even though you don't know x, you can tell whether n is 0. And so that means that power of 3 comma x simplifies. The if statement goes away, and it's just x times power of 2 comma x. And the 2 comes about because we can do this subtraction, right, of n minus 1 if we know what n is. And then now we have another call to power with a constant in its first argument, and we can specialize that over and over again. And eventually you get you're writing new kinds of code. And one thing I'll mention is that this looks a lot like C++ template instantiation. There's a very close connection that template instantiation is, in some sense, partial evaluation. But it's done in a way that is, kind of ad hoc, right? It's outside of the normal language. And so one thing that you'll see here is that this is just sort of, well, if you give a real example in Java, this is just normal Java code, and we're kind of turning that Java code into a template by picking out one of the arguments and saying, you're a template argument in the sense of C++. In C++, you have to do this huge syntactic distinction between the template arguments and the regular arguments. But we shouldn't really need to do that. So what we're really doing here is we're writing new functions. We're writing a power 3 function, and it calls the power 2 function. And so it's writing sort of specialized versions of these functions. And so that was doing it by hand. When we eventually get down to it, we get a definition that power of 3 comma x is the same as power 3 of x, which is just x times x times x. Some terminology here, the code that's left over after doing this kind of template instantiation or partial evaluation is called residual code. And the other thing is that it doesn't always work. If you try and supply the x argument as a constant, but not know n, then there are no computations in here that can be simplified, knowing only x but not n, because all of the computations involving x are connected to unknowns. So it doesn't do any good. So sometimes it works and sometimes it doesn't. Anyway, we can automate this process of doing partial evaluation by writing I showed it yesterday, a p-eval function, a variation of this, that given a function of 2 arguments, and if you know the first argument, it'll actually generate the code of the specialized version of the function. It takes the general function and specializes it to make this specialized function that's a faster version, hopefully, of the original general function. Okay. So I guess I'm going to just mention where I'm headed here now is to do this in Java. So in Java, how are we going to say what okay, so partial evaluation has this idea that some of the values are going to be considered known and other values are going to be considered unknown. But when you have a big Java program, it's not clear what's known and what isn't. So I'm going to let the programmer say, and do this with this interesting new annotation that says compile time. And if there are any really old Lisp hackers in here and they remember, eval when on the Lisp machine or whatever, in the old Mac Lisp, you're kind of doing this similar kind of thing here. This is saying eval when, evaluate this. Well, okay, so I'm creating a compile time string pattern, and then I'm creating a compile time object, a regular expression object, and it says run that at compile time. And the reason why we want to do that is that this is a known class being instantiated with a constant. And so every time you run that in Java, it's going to instantiate the same isomorphic object structure, right? It's going to make the same regular expression object, and it's probably going to do some analysis and code whatever on the regular expression in order to figure out how to run this match or execute function quickly. But every time you run this code, it's going to do the same thing. So part of the idea of partial evaluation is to take those things that happen the same every way and pull them out of the runtime execution and bring them into an earlier phase which I'm going to call compile time. I mean, it doesn't have to be done at the same time as normal compilation, but we already have this earlier phase, so let's just call it compile time. So the intent here is that somehow we would, so what my system does, this Java partial evaluator does, is it accepts code in this form, and when it sees this CT annotation and the compiler is compiling this, it actually loads the regex parser object into the compiler, or some a space that's connected to the compiler, and calls the parse function, to parse the regular expression and create the regular expression object in the compiler. And that might not seem very useful because we actually want it to evaluate on an input buffer that comes at runtime. So now we have these two times going on. The regular expression object exists at compile time, but it needs to parse and match something that's a string that exists at runtime. So what happens is that, well, you can think of this as like the power function, okay? Power function where it's taking the number 3 is the regex, the known thing, and the input buffer is the unknown thing, the x input. And what we want to do is we want to make a specialized version of the regular expression execute method that is specialized to execute this specific string here. And then take that code and put that into the runtime of the program, that specialized method. And if we do it right, all that's needed is the actual methods to do that execution. The actual regex object does not exist at runtime at all. That's kind of the trick, is that the regex is compiled, is instantiated at compile time. It's used to generate a specialized execute method using a general transformation technique that knows nothing about regular expressions. But when it does that, it will generate a specialized pattern matcher for just this string in code without any objects at all, without any regex objects existing. And that's, in a way, that's kind of the ideal, right? That's what you'd expect. And there are all these bytecode manipulation things, and different people have tried to write regular expression parsers that achieve this result by doing bytecode generation at runtime and all this other stuff. But the nice thing about the partial evaluation is that it knows nothing about regular expressions. You just write this, matcher, and then you say, make it at compile time, and it just does it all for you. And so I'll report some results on that in a minute, exactly how that works, and how well it works. But that's the vision. Okay, so the part that I'm going to skip is what I did in the tutorial yesterday, because we're just not going to have time to really go through it if we want to have discussion. But yesterday in the tutorial, and if you want to look at it, I left the slides in because I'm probably going to give the slides to you guys, and you can see them. But basically what it does is it kind of walks through a simple first-order functional language, and then it shows how to do partial evaluation of it in a very simple way. And so, like I said, I did it yesterday. I'm just going to skip it. It's not absolutely necessary to understand that for the details of that to understand this talk. Because what I want to do today is talk more about the implications for Java. Okay, so let's just assume that this mechanism of partial evaluation can work, and what it does is it takes values that are somehow marked as known, and it propagates them through the program, simplifying the code and specializing the code based on those known values. That's the basic process. So it's a lot like a compiler phase that's doing constant propagation. The difference is that the constants can be objects, and they don't have to be constant because they might have mutation in them. And it also happens across method boundaries very aggressively. So anyway, so here's the basic idea. So the style of partial evaluator that I have focused on is called an online partial evaluator, which means that it doesn't do any static analysis. It just sort of runs and makes all its decisions as it executes. But the key thing is that I have some interesting annotations that tell the partial evaluator what to do. And so the programmer is communicating intent. And I'll give you some examples of this. We're not going to get a termination guarantee. We're going to apply it to an object-oriented language. And this is kind of a summary of the whole paper, right? So I'm going to go through these things in more detail in a second. There's a nice formalization of it in Haskell, so you can run it as a runnable semantics and a readable semantics. And then I have a real implementation. And you better be careful with the real implementation. Question?
One question,
Yeah.
You say that object leave either at compile time or runtime.
Yeah.
What about residual program? Does
What?
it leave a residual program? Does it leave a model?
No, an object is instantiated either at compile time or at runtime. And the residual program is what runs at runtime. So it can create objects, or you can create objects at compile time. But an object never gets written into the residual program. It never is. It's just I'll talk about what that means. Does that make sense to you at all? Or yeah, okay. So, so the idea is that there are these two stages. There's the compile time stage, which we're all familiar with. Normally it just analyzes the program. And then there's the runtime stage that's supposed to run the program. Well, this hybrid partial evaluation blurs the distinction because now some of the program is going to run at compile time, and then other parts of the program are going to run at what we normally call runtime. So, so there's really, compile time allows execution of the program. And in some sense, that's already true. I mean, the compiler, even compiler optimizations are sort of, simulating little bits of execution, right? If you have 0 times x in your program, the compiler might look at that and say, oh, I'll run that code. I'll do that multiplication because the answer is guaranteed to be 0, right? So in some sense, it's already selectively executing parts of the program. Those are called optimizations. But in general, they're really just, they're implementing parts of the execution. I have this annotation called CT that takes a normal expression, pretty much anything that you can write, and lifts it and says, run that at compile time. Now, that could fail because some of the inputs that sub-expression E might depend on might not be available at compile time. So you can have this weird situation where you have you've declared a variable that's a runtime variable, and then you try and run something at compile time that uses that runtime variable, and you're essentially getting a time tangling there, right? Compile time things can only depend on compile time things. They can't depend on runtime things. That's the directionality of time here in the staging. So, even though you can, in theory, mark any expression as compile time, it's not guaranteed. You can't just do it willy-nilly anywhere. It won't always work. So here was an example I said that, this will work because this is, a constant. Like I said, if you tried to read the regular expression in from the user as an input and then say compile time regex.parse input, it's going to get an error. The compiler is going to say, I can't run that at compile time because one of the inputs isn't available until runtime. Okay, so that's an example there.
You are expanding the notion of constant expression
Yes.
to specific domains.
Yes. I'm allowing the user to say, treat this as a compile time thing, but it doesn't even have to be constant, is what's funny.
It's like a constrained version of macro expansion.
It's a little bit like macro expansion, yeah. It's got some interesting connections there. One of the nice things about it, as I said, though, is that these things really are just, arbitrary, ordinary expressions. So we're not making a new macro language. We're just kind of lifting the existing language with a subtle distinction in its semantics.
William, if you were willing to run the partial evaluation thing just at one point online and then get the answer without doing something more globally, you could put the compile time, you could compile that, you could express that compile time thing as an invoke dynamic that ran the first time, did your PE inside a bootstrap method, and then bound the result as using a constant combinator to the call site, at which point all subsequent optimization would see a constant.
We do that. We do that in JRuby for regular expressions.
That was way too many concepts that I'm not, immediately fluent in, lumped together in a chain that did not parse. I'm sorry. I mean, I know other people in the room are feeling the same way but aren't willing to say it. But I would love to understand what you just said. So, wait, well.
Once, and then would always use the partial evaluated the next and all subsequent run-throughs.
Invoke dynamic gives you a cut point, which is first time I execute this instruction, do something really expensive, and then
This is at runtime, though.
Yes.
Yes,
It's at
okay.
runtime.
It's a runtime.
So if you're willing to delay the partial
Okay.
until the first execution of the bytecode.
Yeah, so it's true that when you do this, phase is fluid. You could sort of think of partial evaluation not as something that happens at compile time, but happens kind of early on in the program execution. I'm not sure whether, so there's other things that are going to happen here, which I'm just about to talk about. They're more than just it turning into a constant. It has more ramifications besides that. So let's talk about that. Questions? Yeah.
Just to make sure I'm following your line of thinking right. So, but there's an advantage to doing it sort of ahead of time because things like non-termination are less of an issue, and hopefully.
No, I'm not interested in getting rid of non-termination.
No, but I mean, say if I'm running an evaluator ahead of time and it doesn't terminate, it's not a complete disaster. But if I'm running a program in the VM and suddenly the evaluation doesn't terminate, then it's.
No, I'm not trying to, no, the non-termination behavior is not really a goal as far as I know. I mean, it's.
There's a loop in the program, there's a loop in.
Yeah, no, what I'm trying to do is the thing I said early on, that there's very general code, and interpreters are a good example of that. They're very general things that, like the Python interpreter or the Ruby interpreter can do all kinds of stuff. But when you run it, you only run it on usually like you're trying to run some specific program. So there's a classic result that says that partial evaluation can remove the interpretive overhead and just leave the code that you're actually trying to get done without having to do, like in the case of the power function, it gets rid of those if statements. That's what I'm trying to do.
I guess what I'm trying to say, maybe not expressing it as well as I'd like, is that there's an advantage to doing it ahead of time.
There are definitely advantages to doing it ahead of time. The main goal I'm looking at is performance. Yeah, potentially, orders of magnitude performance improvements. So, and one way of looking at it is that anything you do, if you have some code in your program that every time the program runs, it does the same thing, why not do that in advance? In some sense, right? If it's sort of, it's redundant. So here's some examples. So let's just say that this config object had previously been declared as config equals compile time load, config file. Okay, so that's a stateful object that's going to load a config file off disk and parse it and make a config object, right? We do this all the time. We have these runtime config objects, and then we say things like, if config.logging enabled, then do some stuff. Well, one of the interesting things about this, if you partially evaluate it, is that this config object doesn't exist at runtime anymore. It now exists in a compiler. And so when you say config.logging enabled, it has to run that method in the compiler. So one of the rules is that if you have a compile time if you have an operation or an expression that involves a compile time object, you have to run that whole expression in the compiler because that's when the object exists. And so it propagates. Once you make a compile time object, everywhere it goes, it's like a little enzyme. It starts causing code to have to run, right? And so this logging enabled, the compiler will ask the logging object, is logging enabled? And it will say yes or no. And then this code will just be eliminated, right? So it's like an if-def.
I'm interested in knowing whether you can have some sort of strange dependencies between compilation and execution. For example, if you have certain condition under which you need to run things that you haven't compiled yet.
Oh, yes. Okay, so he's jumping ahead. He's saying, how do I run the config object if I haven't compiled it yet? All right, so the way this works in the current prototype compiler, it actually does a two-phase compilation strategy where it compiles everything normally, and then it goes back and recompiles and reruns the things. So yeah, it needs an instance of the config object, the code for it. So it's done that first, yeah. And it's not very smart the way it does that right now. But it'd be nice to do that more intelligently. So you can do this, you can say config enabled with a string here too, and that's just fine as well. It'll go in and into the config object and ask it using this constant string is logging enabled, and that'll also do dead code elimination. This one's a little more interesting. If config.enabled user input. So this is, again, you have to start thinking of this distinction between compile time and runtime, and when an operation involves both compile time and runtime information, what happens? Now we're trying to do something that it's I've told you that objects only exist in one phase, and so how do we deal with operations that seem to blend those phases? And so what happens here is that, well, essentially it has to inline the enabled method using, and when it does that, it uses all of the static information, all the compile time information in the config instance that actually exists at that moment, right? It's a real object in the compiler, and it sort of runs the enabled method, and anything that it refers to the config object will get kind of inlined into that method, and anytime it refers to this unknown thing, it'll just emit the code necessary to make that check. So it is, it's actually possible for this to fail at compile time, it's called the binding times. The time that the things exist, violate the rules of time travel, basically. And so it doesn't work. But if the config object does the normal thing, which is it tests if the input is equal to a couple of different strings, or looks it up in a hash table that it previously created from static information, then it can, it can probably, it'll produce output by this kind of inlining style. And the reason it has to do this is what it's essentially doing is it's saying this object has to go away. Anything that's declared and created at compile time has to exist in the compiler and then not exist at runtime. And so the only way that we can have a method on a thing that doesn't exist be able to run at runtime is to take that method and kind of lift it out of the object and put it in. It actually writes it as a static method. It makes a new kind of static method for that thing. So the object instance doesn't exist, but its kind of residual effects are there in that method. Does that make sense? So you can also use these config objects, and like I said, they're like these enzymes, so that wherever they go, they cause this specialization, residualization to happen. So if you pass one of these compile time objects to a constructor, then what happens is that, again, this config object has to go away because it's compile time. So the only thing we can do is burn the config object into a version of this system class and specialize the system class for that particular configuration. And then, so it'll make a new system sub 1. And then when you do it for config 2, it'll make a new system sub 2. And it'll make 2 of these system objects that both have the sort of whatever configurations are loaded into them. And that causes problems for reflection, for example, because now these new classes are being created. So, there was a discussion earlier about reflection. It's like, oh, well, we just borrowed the Java reflection API, blah, blah, blah. It's like, nobody can go wrong buying IBM or whatever, right? It's like, I just did what everybody else did. Well, the Java reflection API really sucks, basically. And in the sense that it violates encapsulation, right? And it makes, it's useful for a lot of things, but this idea of being able to ask an object, what class are you, and get an actual answer without it being able to refuse or claim to be different is a little difficult. So I guess I believe in the notion of object-oriented programming as fundamentally almost simulation. Going back to Simula, any object should be able to pretend to be any other object, and you shouldn't be able to tell the difference. That's one of the kind of characteristics of object-oriented programming, right? That you can always substitute somebody else who does something fancy, and no one should be able to tell the difference. Well, reflection is a way to tell the difference. Instance of is considered harmful in my book, right? That's a bad thing. And maybe you should ask the class, ask the object, what instance are you of? And if it could lie, then I'd be happy. One of the fundamental characteristics for me of object-oriented programming is the ability to lie consistently about everything. And if you can't lie, then it's not good. So that's why I say reflection is bad, because it doesn't allow classes to lie.
So reflection, if we're done with views or mirrors,
Yeah, then it's fine. Yeah, right. That's why those things exist, is to give a more clean object-oriented view of reflection. And so I'm not against reflection. I love it. But I just think it needs to be done carefully.
Why don't you allow compile time objects live in runtime?
Why don't I allow compile time objects to live at runtime? That is it's a design choice, right? Most previous partial evaluators do support the idea that complex objects that get created during partial evaluation time can migrate and exist at runtime. People like that from an academic point of view because it gives more completeness. The partial evaluator fails less often, right? It always produces code that will run and produce the same answer. I don't like it because it is almost always wrong in my sense, okay? If I want this residual expression object to be, or my AST, let's say we're doing an interpreter, and I want the AST to be compile time, okay? And I want to interpret it. Having the AST suddenly jump and live at runtime is definitely wrong. I mean, you don't want that. The whole point was to get rid of it. And so, so I've sort of made an engineering decision that's part of the predictability. When you say compile time, it's guaranteed to be compile time only. And that's something you have to live with. You can argue that that's wrong, but I'm pretty certain that it's right from a pragmatic point of view. But it's a...
But actually, your compile time objects migrating to runtime via inlining or specialized classes.
The pieces, the code from them and some of their little guts are migrating, but the whole identity, the object identity isn't. So I'm okay. Obviously values, primitive values can migrate, strings and integers and things. And code can migrate. I just don't allow object identities. And one of the reasons is that I would have to, it would be really hard to do as well. You'd have to take the object and somehow serialize it into the source code of the residual program, right? Which isn't a very normal thing to do anyway in Java.
And then you would actually have to create and reify it.
You have to create it and reify it at the right time at runtime, which is what I want to avoid in the first place. So I'm, you know, this is like one of the fundamental things that is a design decision that I'm kind of betting the horse on, betting the farm on, but it's the kind of thing that everybody looks at and just thinks is stupid at first, you know, especially people who really know partial evaluation. So, so I don't know. It's a design decision. I can't prove it, but anyway, yeah. So it specializes, and then here's a case of a dynamic hash map that you try and put under some identifier the config object. That's a compile time thing, and that generates a compile time error because in your source code you said config is compile time, and then you tried to store it into a dynamic collection, and it just doesn't exist at the time when the dynamic collection exists, and so that's not possible according to my rule, and so that's an error.
Presumably you could warn and backtrack and undo your work. But...
Well, in a sense you do, because you say compile time error, and that tells the programmer either he can't say compile time on that thing, or he can't put it into that collection. He's got to do something different. So the compiler can't tell what to do, but it can tell that there's something going wrong, according to my view of what wrong means.
Yeah, what I'm saying is it would be safe to optionally
not make it compile time.
Not make it compile time.
See,
or bail out.
Yeah, but see, that would reduce the predictability, because when you say compile time, you're expecting some specific behavior there and performance. And so I would actually view that as an error in the compiler to make that assumption.
Should we throw an exception with a residual program as an argument?
Well, we don't have compile time. I mean, I don't know what this notion of compile time exception handling. I don't know. I don't know who would be there to catch that error. Right now, the programmer catches it. It bubbles right up to the programmer.
So this comes to me as something of a surprise, because there was the whole compile time code generation part that made perfect sense. And as you were talking about regular expressions and other types of domain-specific constants, I was thinking of all of Mike Ernst's pluggable type checking work.
Okay.
Which overlaps in many of the, I'm looking at the list of domains that he has static type checking for, regular expressions, property files. It's clear there's some connection there. And of course, this compile time type checking now that you have now added in is very, very similar. You're using a value which is marked as compile time tainted in some way, and you're trying to use it. So that, I mean, it's all great. It's just that these are two very different worlds traditionally.
Yeah,
and
yeah.
You're fusing them.
Well, I think that, yeah, so there might be a connection between type checking in general and partial evaluation, but we will probably have to talk about this offline. So yeah, it's an interesting question.
I'm trying to predict your next sort of specialization by looking at his list of type checking.
Right.
One so far.
Okay, so I have this policy that I have imposed to simplify things and make them more predictable is my goal, so that it does what you say it does, and it always does it. And if it can't do it, you get an error. And the policy is that objects exist in one stage, they can't move, primitive values can move. That's arrays? I don't think they can move. Strings can move. Yeah. Honorary primitives. I think of strings as primitive. Dates can move too, I think. Basically value types. Yeah. Yeah, I mean, it's kind of an accident that, the strings don't, look like int in Java, but from my point of view, they're basically primitive. Okay, so that's the policy. It works for you or it doesn't. You get what you get. Okay, so let's talk about mutable state a little bit. So, yeah.
You said date moves, even though Java util date is mutable?
I actually don't know whether dates move, but I didn't know that they were mutable. Are SQL dates mutable?
Yeah.
Really? Yeah.
They are a subclass of Java util date.
Well, there's probably I'd have to check. There may not be an actual restriction that mutable things cannot move. I don't know if that's an issue. It might be. Part of the issue is just the ability to serialize them cleanly into source code. At least dates can be serialized in some sense. The problem is identity. Once you have mutation, you have identity. And so you can get into issues. And actually, if it's mutable, we're going to run into trouble because of this. So what happens is that we support mutable state. The programs that are being partially evaluated can be fully imperative because Java is fully imperative, and that's what we're working on, right? So as I said, objects are always compile time or runtime. And so what happens there is that when you make an object be compile time, it runs like a normal object, and it can mutate itself, and it can mutate other objects, and it can create them. It just is running very happily at compile time, doing all the normal things that it can do. And the mutations occur in the right order. And then when the runtime objects obviously get created, and they mutate very happily. But the mutations that occur in compile time and the mutations that occur at runtime aren't necessarily sort of sequentially consistent with the original program. So if you run the program by erasing the CT annotation, let's think of it that way. In a lot of cases, the program will run the same, okay? But it's not guaranteed because when you say CT, that means that you're lifting some of those computations out of the runtime execution into compile time execution, which can reorder the effects, right? The effects that happen at compile time happen in the right order. The effects that happen at runtime happen in the right order, but they don't necessarily happen in the same way with respect to each other across those domains. So you have to be careful with that. And as a result, the behavior can actually be different. The program can behave differently if you take it and you erase the CT and run it, or if you have the CT and run it. A lot of programs might work the same, but there's no guarantee that just erasure, that erasing CT. So CT is not a completely no-op semantic operation. Okay, if you have a print statement, if you say CT print system.out blah, then that system.out will happen in the compiler, and it'll tell the user of the compiler, warning, blah, blah, blah. If you don't have it, it'll happen to the user, right? It's just not the same.
So wait, is system.out a compile time variable or a runtime variable?
Well, okay, so the point is that when you say CT, it means run this in the compiler, and as long as the resources available to run it in the compiler are available, it will run it in the compiler. And system.out exists in the compiler. A definition of system.out exists in the compiler, and so it can do that. It's not the same system.out as the one in the runtime program. So that's what I'm saying, is that CT makes the program mean something different. It's a different programming language a little bit when you add CT. It has different semantics. Yeah.
Technical question. CD can be written only over an expression.
Right.
Right. So I cannot put a bunch of statements into it.
You can put those statements into a method.
Yeah.
And then call CT on it. Yeah. Yeah, that's just sort of a syntactic limitation, that there's no way to wrap blocks with code.
I guess another difference is when you compile against a version of the JDK and you run against a different version. behaviors?
You could get different behaviors, yes. Yeah, because you've got two runtimes now. The behavior that happens in the compiler versus the behavior that happens in the runtime. Yeah. Yeah. Okay, great. Okay, so we're good. I just want to mention reflections, kind of fun. If you do a reflective thing, like, and here I'm saying CT get size. So this is making a compile time string. And we then call o.getClass.get method of name and invoke it. Under the right circumstances, that'll just turn into o.getSize in the residual code. There's kind of a special case there that knows that that just is true. It's kind of fun. No termination guarantee. We talked about that. That's already true of C++. So
True for Java as well, so don't worry.
I was debating that, whether Java is truly able, does the Java compiler, can it really diverge?
With certain cases.
Certain cases with subtyping or something? Yeah, okay. Well, now you get more cases. So, right, you shouldn't, once you let the cat out of the bag, you know, get a few more cases, you shouldn't be unhappy, right? You're already dealing with it. Okay, so I have an example here that I'm going to skip, which illustrates how partial evaluation would work on a simple state machine interpreter. So if you make these state machine objects in memory, and then you interpret them by, doing the standard thing of looking for transitions and stuff, it'll specialize those and make, well, we can do the summary real quick. Here's the actual interpreter. Actually, there is really one important point I want to mention here. So I'm going to go back. Here's the interpreter, and then here's the residual code operating on this. So, but this is the data structure, the constant objects that represent a two-state state machine with some transitions. Okay, so imagine a sort of in-memory representation of that. Here's an interpreter that interprets that state machines in general. But when you interpret this particular state machine with this particular interpreter, it generates this code where it makes a run open. So it makes a run state for a run method for each of the different states in the machine. And then it checks just constant, is the input equal to close, which is the name of the hard-coded, particular thing in the actual state machine. And if so, it runs close. Otherwise, it goes back and runs open. And this is the case that Guy Steele was talking about as well, of wanting tail call elimination. So anyway, so this is the specialized version that you get as residual code from specializing the generic state machine interpreter against a specific in-memory state machine representation. Okay? So it's kind of, it's good for that kind of thing. And we write that, so it's analogous to the regular expression example. Okay, I'm going to skip this one too. We've done some experiments with like web frameworks, which are also interpreters, and fun stuff like that. So let me just very briefly, for humor, mention that the student called his system Sidit. Has anybody heard of civets before? They're little creatures that exist somewhere in Madagascar or something, and they eat coffee beans. They love coffee beans. Here he is eating some coffee beans. And he only eats the fruit around the coffee bean. The actual coffee bean part, the seed in the center, passes through the civet's digestive system and is pooped out as a solid coffee bean. And it turns out there are people who go and collect civet poop,
And it's super expensive.
extract the coffee out of it, washing it off and stuff, and then processing it into coffee. It's like $1,000 an ounce. It's the most expensive coffee in the world.
The coffee's been partially evaluated.
It's been partially evaluated, yes. Exactly.
And it's only better.
And it's very precious, exactly. So that was like the most brilliant name ever of a software system. He needs a prize just for that. And okay, so the darn thing actually does some fun stuff. We ran it on a third-party product called ModelTalk, which is like an interpreter of configurable pricing algorithms, where you can have a data file that says what the pricing algorithm is, and there's a little engine that does the pricing implementation. And when you normally run the thing, it's really slow because it loads in the pricing table and then it interprets it. Well, when you run Sidit on it, the pricing table gets loaded in, and the algorithm gets specialized, and so you just get hard-coded rules, and it runs, an order of magnitude faster. So.
How big of a framework is that?
Oh, we took this actual framework is quite large. we took a kind of mini version of it for the experiment.
But the key aspect is that your configuration file are really programs, constant programs in a DSL, which can be
Yes.
evaluated.
Yes. Yeah, so it's using the same basic pattern, yes, of DSL. Configuration files are DSL, exactly. We also did it for the Regex example. So this is a fairly complicated Regex, and the original unoptimized state machine Regex time is really slow. There's a specialized one is pretty fast, and then there's a hand-tuned bytecode generated by hand, Bricks Regex library that's actually slower than our naive guy. So that's kind of fun. And let me just mention sort of the paradox of partial evaluation, which is that if you have a naive, slow version of your program and you work like crazy to hand optimize it, you can do that, putting in hash tables and caches and all this other stuff, but you can't ever really know the specifics. You're still writing a general purpose program. You can't know the specifics of what this algorithm is doing in a lot of cases. This is for algorithms that have this characteristic that they have some data that doesn't change and some that does. The weird thing is that what I've seen is that if people often write these hand-optimized versions naturally, we hate slowness, so even if you aren't caring about speed, you'll still write this. You often have to de-optimize it to get the partial evaluator to work. And then when you partial evaluate it, it becomes 10x faster than the one that you got by partial evaluate. Let me actually.
Runtime annotation for your cache.
Well.
Undo the compile time annotation.
Yeah, let me just mention this, because there was a thing in here that I skipped over that I really should mention. Here's an original version of this state machine interpreter, and what it was doing is it was taking the current state, taking its transitions, which is a hash map, and looking up the input in that hash map to compute the next state. So this is a hash map from strings to states. It tells it where to go next, and that's a typical kind of fast lookup, right? And unfortunately, the partial evaluator will choke on that. Because it is trying to look up a dynamic input in a compile time hash map, and the compile time hash map doesn't exist at runtime. So it's one of these phase shifting problems. And so you actually have to de-optimize the interpreter and turn that hash lookup into a linear search. Yeah. When you turn it into a linear search, it untangles the binding times because it can now unroll this loop in the partial evaluator and then write a check for each of these different cases. It turns into a switch statement, basically.
Why can't you unroll the hash table?
Well, I've considered adding sort of special case for hash tables. I haven't done it yet. I don't know whether that would work exactly, but this is a general pattern of a problem with partial evaluators in general, and it's called the trick. That's the technical name for this fix. And it involves taking, it's called binding time improvement. It involves taking some code that has sort of data structures that tangle the different times of binding, and often writing it in a slower version that untangles those, that then will allow it to produce the fast code. Question, yeah.
If the state is represented as a matrix,
Yeah.
or going to a string to a given next state, is that any better?
A matrix?
Yeah, like an array of arrays.
Yeah, as long as it's not a hash map, as long as it's doing a linear search. Essentially, yeah, I need to just wrap up. So anyway, I just want to mention that sometimes programs that you think are going to be really fast and nice, and the programs that you'd naturally write don't partial evaluate correctly, and you have to write a stupid program instead that makes the partial evaluator fast. So that hence my kind of, I call this the leapfrog diagram, right? You make your program slower in order to get it to be faster. And that's nice because sometimes these slow versions are really simple and easy to understand. They don't involve all kinds of tricky optimizations. We leave the tricky optimizations to the partial evaluator. Okay, future. What's that? I know. Okay, we're done. Okay, so just want to mention that currently it's AST-based. It ought to be bytecode-based probably, so that's a future work. And in conclusion, you put in annotations, you get controllability. You don't get a lot of guarantees, but you do get sort of a guarantee that it will do what you said you wanted, and if it can't do it, it tells you. You get an error. Okay?
Any performance measurements?
Oh, I had a few. Did I skip over them? This was that one. Faster than hand-tuned regex library. And that one, faster than other code. So there's some more in the paper. But yeah, it's probably needs more benchmarking. OK, thank you.